All right, so I want to look at two useful theorems. The first one is one that you've essentially seen before, but I'm going to say it in slightly different language. So polynomial, rational, radical, and trig functions are all continuous on their domains. You pick a point that's in the domain of any one of these types of functions, and you know that it's continuous at that point. In other words, it has the direct substitution property. So this theorem is telling you that if you want to take the limit as x goes to a of f of x, and you know that f is either polynomial, rational, radical, or trig, and a is in the domain, then this will always just be f of a. So this is giving you the direct substitution property that we talked about before, but in a slightly different language, in the language of continuity. What's a radical function? Well, it's a function involving like square root of x or the fourth root of x. Those kinds of things are radical functions. And the second theorem says, look, if you have a constant c is just a number, it's an element of the reals, it's a number, and I have two functions that are continuous at a, then their sum and difference, their product, their quotient, and also multiplying by a constant, all of these combinations are continuous at a as well. And why is that true? Well, it follows immediately from the limit laws that we talked about before. Once you know that f and g are continuous at a, that's giving you a statement in terms of limits. And then we said that, look, when you add, multiply, divide, or multiply by a constant, then the limits behave very nicely as long as you know both limits exist. And so if you want to think about how you can see this statement from the limit laws, I would encourage you to do so, but it shouldn't be too hard to see how it follows immediately. Okay, so let's write down two examples. So the first one, I've written the function down for you, and I realize that I can write down the limit as x goes to not anything that I want, but almost anything of this function. The only thing that I really don't want to consider is 2, because this function 2 is not in the domain of h of x. Let's actually jot down that the domain of h of x equals what? Minus infinity to 2 union 2 to infinity. 2 is the one thing you can't plug in. H of x is a polynomial plus a trig plus a rational. And so by the previous result, since you know this is continuous on its domain, this is continuous on its domain, and this is continuous on its domain, then the sum is going to be continuous on its domain as well. And so, for example, we can talk about the limit as x goes to, to 1 of h of x. You automatically know that's h of 1. Whatever h of 1 is, that's what this limit is. You can compute and say, well, h of 1 is 1 plus the sine of 1. And then what are we going to get here? We're going to get minus 1, so it's just sine of 1. All right, and again, I could put lots of other things than 1. The only thing I couldn't put here is 2. I just chose to do 1. Let's do another example. This is a limit that I'm handing you, and I'm saying, please compute it. And you take a look at this function, and you say, well, that's a rational function. It's a fraction of polynomials. 3 is in the domain of this guy. What's the domain of this function? The domain of this function is everything except, where the bottom is 0, everything except negative 5. And so you know that this limit is the same as if you just plug in 3. This is going to be 9 minus 12 over 8. So what is that? Negative 3 over 8. All right, so let's look at one more theorem and one more example, maybe two more examples. So the next theorem says that if f is continuous at x equals g of a, whoa, what's going on? And g is continuous at x equals a, then the composition is also continuous at a. What is that really saying? Here's the heartbeat of what we're really trying to say here. If you take the limit of a composition of two functions, and you know that the outside function is continuous at g of a, right? That's what I'm assuming. Then you can pass this limit inside. This full limit is the same as f of the limit as x goes to a of g of x. And by the way, we're assuming g is continuous at a, and so this limit you know is just g of a. And so this, you can jump to here. this limit you can just plug in as long as everything is continuous in the right sort of way. Now, it's all fine and dandy to write down statements like that, but you need to be able to use this in practice. And so let me show you two examples of the kind of things that I'll expect you to be able to do. So the first example, you know what, I'm going to shift some of this stuff around here. Let's put that there, and we'll put our little a symbol over here. Okay, first example. I want to take a limit as x goes to 2 of this, function, and I see, well, I know that cosine is continuous everywhere, and I know that x squared is continuous everywhere. So if I want, I can just immediately plug in. I can say, well, okay, then this is going to be cosine of 2 squared, which is just cosine of 4. But it might be helpful for you to realize the intermediate step, and that is you can think about this limit as the cosine of the limit as x goes to 2 of x squared. I don't typically write this, but that's how I'm thinking about it, is this function is continuous at x squared evaluated at 2, and so I can sort of pass the limit inside, and I get to here. So that's up to you whether you want to write that or not. Let me add a little dividing bar here so we can keep these problems separate. Something like that. Okay. And then here's another example. So I give you this function, and I ask you to compute its limit, and you say, well, okay, wait a minute. This is a rational function, and then I'm plugging in some trig functions. This function is going to be continuous on its domain. Actually, this domain is everything. There's nothing you can't plug in here. I claim the bottom is never going to be 0. Why is that? Well, the worst case scenario is when cosine is -1. That's the most negative cosine can ever be. And so I can get a -2 sitting here, but I've got a 5. I'll never pull the bottom below 3, actually. And so this function is defined everywhere, and I can see that it's just a function composition, and so I can just plug in. I can immediately plug in and say, well, this is just sine of pi over 5 plus 2 cosine of pi. And what do we know about sine of pi? Well, that's just 0, and so I get 0. I'm done. All right, so we'll end this video here, and I want to end by looking at one more useful fact. It's called the intermediate value theorem. So we'll do that in the next video and then wrap this lecture up.